Ever pondered how data is stored and accessed in computer science? Today we're going on a journey to explore that. We live in a world where data is as valuable as gold, and knowing how to store, access, and manipulate this data is an essential skill in computer science. This brings us to the concept of data structures. Data structures are specific ways in which data is organized to be used efficiently. Think of them as the storage units of the digital world, each with its own unique blueprint and purpose. There are numerous types of data structures, each designed to handle data in a specific way. One such type is the array, a simple yet powerful structure that stores data elements based on an index. We also have stacks and queues, which follow the last in first out and first in first out principles respectively. Then there are trees, which store data hierarchically, and graphs for data that doesn't follow a specific order. But today, we're going to delve into the world of linked lists. Imagine a chain where each link holds a piece of data and points to the next link. That's essentially a linked list. There are several types of linked lists, such as singly linked lists, doubly linked lists, and circular linked lists, each with its own unique properties. In this video, we will focus on one particular type, the singly linked list. It's a fascinating structure that consists of a sequence of elements called nodes, where each node contains a data element and a reference or pointer to the next node in the sequence. It's like a one-way street of data, where each stop has something to offer and points you to the next stop. So buckle up as we embark on this exciting journey of data structures, starting with the singly linked list. By the end of this journey, you'll have a clear understanding of how this structure works and why it's a fundamental part of computer science. Let's dive right in. So, what exactly is a singly linked list? Let's break it down. In the realm of computer science, the singly linked list is a fundamental data structure. It's like a chain, where each link is made up of two parts, a data element and a reference to the next link. We call these links nodes. The reference or pointer in each node directs us to the next node in the sequence. When we reach the final node, its pointer typically points to a unique value, let's say null, to signify the end of the list. Now, think of the singly linked list as a scavenger hunt, where each clue leads you to the next. The head pointer is your first clue. It points you to the first node or the starting point of your list. From there, you follow the pointers from one node to the next until you reach the end. Each node in this list has two parts. The first part holds the data. This could be anything: a number, a character, a string, or even a more complex data structure. The second part of the node is the pointer. It's like a signpost that points the way to the next node in the list. You might wonder why the last node points to null. Well, null is a special value that indicates the end of the list. It's like the finish line in our scavenger hunt. When we reach a node that points to null, we know we've traversed the entire list, and there are no more nodes to visit. So that's the singly linked list for you. A sequence of nodes, each holding data and a pointer to the next node, kicked off by a head pointer and wrapped up with a pointer to null. It's a simple yet powerful data structure that forms the backbone of many complex algorithms and data manipulation techniques. Now that we understand what a singly linked list is, we can explore how it operates. Singly linked lists are dynamic, and we can perform several operations on them. Our journey through the versatile world of singly linked lists continues as we delve into the essential operations you can perform on them. Imagine you've got a string of linked nodes, and you're the conductor, orchestrating a symphony of data manipulation. Let's start with the insertion operation. Picture yourself as an artist, adding a dash of color to a linear canvas. You can insert a new node at the beginning, placing it as the new head of the list. Or you might prefer to add it at the end, extending the list a bit further. Sometimes you might want to insert a new node after a given node, slipping a new detail into the middle of your data sequence. Next, we have the deletion operation. Imagine you're a sculptor, chiseling away to achieve the perfect form. You can delete a node from the beginning, shifting the head of the list to the next node. You can also delete a node from the end, trimming down your list. Or you might need to delete a node after a specified node, removing a specific detail from your data sequence. Then we have traversal. This operation is like taking a leisurely stroll through your list, visiting each node in turn. You can access or modify each node's data as you pass by. The search operation is your detective work. You're on the hunt for a specific value within your linked list, following the trail from node to node until you find your target. Finally, the size operation lets you assess your list at a glance. With one swift calculation, you can find out the number of nodes in your linked list, giving you a sense of the scale of your data. These operations form the core functionality of singly linked lists. They allow you to manipulate and explore your data, shaping your linked list to suit your unique needs. With these tools in your data structure toolkit, you're well equipped to tackle any challenge that comes your way. Like any data structure, singly linked lists come with their pros and cons. Let's delve into what these are. First, let's discuss the advantages. One of the most significant benefits of singly linked lists is their dynamic size. Unlike arrays, which have a fixed size defined at the time of creation, singly linked lists can grow or shrink dynamically as elements are inserted or deleted. This flexibility makes them a perfect choice for situations where the number of elements is not known in advance or can change over time. Another advantage of singly linked lists is the efficiency of insertion and deletion operations. When adding or removing an element at the beginning of the list, these operations can be performed in constant time, denoted as O(1). In contrast, these operations in an array might require shifting elements, which can be time-consuming. Now, let's move on to the disadvantages. The first one is sequential access. Unlike arrays, singly linked lists do not support random access to elements. To access a specific element, you need to traverse the list from the beginning. While this might not be an issue for small lists, it can become inefficient for larger lists, where the element you're looking for is towards the end. The second disadvantage is the extra memory overhead. Each node in a singly linked list not only stores the data element, but also a reference to the next node. This additional memory requirement leads to more overhead compared to arrays, which only store the data elements. Despite these drawbacks, the flexibility of singly linked lists makes them invaluable in many scenarios. The key is to understand where they shine and where other data structures might be a better fit. In the next section, we will explore how to implement a singly linked list. Stay tuned. Now let's see how we can implement a singly linked list in Python. In Python, we start by creating a node class. Each node in our list will be an instance of this class. The node class has two attributes, data and next. Data is where the actual information will be stored, and next is the pointer that will lead us to the following node. We then move on to creating the singly linked list class. This class will be used to implement the operations on our list. The head attribute is initialized as none. This will be updated to point to the first node once we start populating our list. Let's start with the insert@beginning method. This method creates a new node and places it at the start of the list. The next attribute of this new node is set to whatever node the head was pointing to earlier. Then, the head pointer is updated to point to this newly created node. Moving on, we have the insert@end method. This method is used to append a new node to the end of the list. It first checks if the list is empty. If it is, the new node is set as the head. If it isn't, it traverses the list to find the last node and updates its next attribute to point to the new node. Finally, we have the display method. This method traverses the list from the head till the end, printing the data in each node. Once it encounters a node with next attribute as none, it prints none, signifying the end of the list. So after creating an instance of singly linked list, we can use insert@beginning and insert@end to populate our list, and display to print it. And there you have it, a basic implementation of a singly linked list. With this, you can start creating and manipulating your own lists. Output.